Bit Simply 5. Learn, loop, evolve.
Welcome back. In the year 1954, commercial flight was finally moving beyond the altitude and speed limits of propeller engines. The de Havilland Comet represented the peak of British engineering. It was designed to fly significantly higher and faster than any commercial airliner before it. Inside, passengers enjoyed high-end luxury, eating hot meals on real china while looking out at the stratosphere through the plane's signature feature, large, square windows. But 20 minutes into a routine flight from Rome to London, while cruising at 27,000 feet, the plane vanished. There was no distress signal and no warning of a mechanical failure. Months later, a second comet disintegrated mid-air under similar conditions. Global panic followed, and the entire fleet was grounded. The same technology that allowed the comet to fly higher also subjected the airframe to pressures that engineers had not yet fully encountered. A structural flaw was hidden within the design. Winston Churchill ordered a massive recovery effort. Naval teams spent months fishing thousands of pieces of shattered aluminum out of the Mediterranean Sea. At a hangar in Farnborough, engineers began the process of piecing the jagged metal back together on a custom frame to locate the source of the failure. To test their theories, they submerged an entire intact comet fuselage in a giant water tank. This allowed them to simulate the pressure cycles of thousands of flights in a controlled environment. They ruled out engines, ruled out bird strikes, and ruled out explosives. With mechanical failures off the table, the investigation shifted focus toward the structural geometry of the fuselage. To understand the failure, we have to look at the fuselage as a pressurized vessel. It is designed to keep the cabin air thick enough for humans to breathe while flying in a vacuum. Inside, air pushes forcefully outward against the metal skin. Outside, there's very little air pushing back. This causes the metal to physically breathe. The fuselage expands as it climbs and contracts as it descends, creating a rhythmic cycle of stress. Propeller planes typically flew at altitudes where this expansion was negligible. The Comet, however, reached the stratosphere, where these pressure cycles became much more intense. This constant cycle of expansion puts the airframe in a state of permanent tension, turning the internal air pressure into a force that tests the integrity of the metal skin on every flight. Engineering math shows that in a perfectly smooth, round tube, this stress is distributed evenly across the surface, flowing like water through a pipe. Cutting a hole disrupts this flow. With sharp corners, stress cannot flow around easily. It piles up. In the Comet, stress concentrated in the square window's 90-degree corners, reaching levels 3 times higher than the rest of the fuselage. This concentration of force led to a condition called metal fatigue. This process involves the formation of microscopic cracks in those corners. Each time the plane pressurized during a flight, those cracks grew a fraction of a millimeter. Eventually, the metal reached its limit. A crack would race across the fuselage at the speed of sound, causing an immediate loss of structural integrity. The math confirms that the shape of the window was the deciding factor. A sharp angle placed under rhythmic pressure creates a structural vulnerability that will eventually lead to collapse. The solution to this atmospheric pressure problem was to round the corners of the windows. An oval shape allows the stress to flow continuously. By removing the 90-degree corners, engineers ensured that there was no specific point for the force to concentrate and tear the metal. The investigation into the Comet led to a new approach in aviation architecture called fail-safe design. Modern airliners have almost entirely eliminated sharp 90-degree angles. You can see these curves on cargo hatches, passenger doors, and even the internal brackets holding the plane together. Airplanes are also built with ripstops, heavy titanium bands that circle the fuselage. If a crack does start to form, it can only travel a few inches before it hits one of these bands and is forced to stop. The square windows of the Comet weren't the result of negligence, but of engineers discovering the limits of materials in an environment where they had never been tested before. The curve of a modern airplane window is the result of those 1954 investigations. It is a shape designed specifically to maintain the structural integrity of the cabin against the vacuum of the sky. Thanks for watching. For more on the engineering of the jet age,